Hi all, I am Lavani Singla and welcome to my channel Masters the Concept. So let's have a look at today's problem. In this video, we will understand Prim's algorithm. So let's understand what is a Prim's algorithm. Prim's algorithm is a method used to find the minimum spanning tree of a connected weighted graph. So to understand Prim's algorithm, first we need to understand the minimum spanning tree. So let's have a look at MST. A minimum spanning tree is the smallest acyclic tree that connects all the vertices in a weighted graph where the total sum of the edge weights is minimized. To learn more about spanning tree and minimum spanning tree, you can watch my video on spanning tree. I have provided the link in the description of this video and also now reflecting in the right top corner of the screen. Now let's understand Prim's algorithm in depth from this graph. Suppose we have this graph and for this graph what will be the MST? So let's see. As per the definition, the minimum spanning tree contains same number of vertices of the original graph. So let's have all the vertices here 0, 1, 2, 3 and 4. And we will have these edges 0 to 1, 1 to 2, 2 to 3 and 0 to 4. So for this graph, this will be the minimum spanning tree and these will be the weights 2, 2, 1 and 1. The total sum of the weights will be 2 plus 2, 4 plus 1, 5 plus 1, 6. 6. So this 6 we can call MST of weights. So Prim's algorithm helps us to find this MST of weights and edges involved in the MST. For example, for this MST, the edges that are involved are 0 to 1, 0 to 4, 1 to 2, and 2 to 3. So with the help of Prim's algorithm, we can find the list of the edges involved in minimum spanning tree and the total sum of the weights of all the edges. Now let's understand the approach of Prim's algorithm. To start with Prim's algorithm, we need some couple of things. First, we need a priority queue. So let's have a priority queue. Why I will tell you. And one, we need a visited array same of the size of the number of vertices. So here we have 5 vertices. So let's have 5 elements here. Again, I will explain why we need this. And with this, we need a MST list, which will contain the list of the edges of the MST. This priority queue will store weight, node, and its parent. And for this visited array, initially as we haven't visited any nodes, so we will mark all the nodes as unvisited. We can take it as an integer array or a boolean array. So if we are taking it as integer array, so we can mark a visited node with 1 and unvisited node with 0. And if we are taking it as a boolean array, then we can use true and false. Because I'm taking it as a boolean array, I will set the value for all nodes false because we haven't visited any node yet. So now we will start. We can start from any node, either from 0, 1, 2, 3, any node. Here I am starting from the 0th node. So for 0th node, I am taking the weight 0 and node is 0 and the parent I am taking -1. Remember one thing, we have inserted one element in priority queue, but we haven't marked any node as visited. First, we will start iteration over this priority queue. Then we will start marking the nodes as visited. So now we will take out one element from this priority queue. So that is 0, 0, -1, this node. And we will mark this node now visited. So this is visited now. So we will mark it true. As parent is -1, so we will not insert this edge in this MST list. Now we will look at the adjacent neighbors of this 0th node. So from 0, we can move to 4 and 1. So we will insert 1 and 4th node in this priority queue with their corresponding parent and weight. From 0, we can move to 1 with weight 2. So we will insert 2, 1 node and the parent is 0. Similarly, we will insert for 4th node. So from 0, we can move to 4 with weight 2. So 2 node is 4 and parent is 0. This we have removed. Now we will take out the another element from this priority queue with minimum weight. As both nodes have the same weight, so we will get this from the priority queue. So weight is 2 and the node is 1 and the parent is 0. So now we will insert this edge in this MST list. So 0 comma 1. And we will mark this first node as visited. So we will mark it as visited. And we will add this weight to our MST sum, total sum. So initially sum is 0. So we will add 2 in the sum. Now we will look at the neighbors of this first node which are not visited. So from 1 we can move to 0, but 0 is already visited. So we will ignore 0. So from 1 we can move to 4, and 4 is not visited yet. So we will insert 4 in this priority queue with the weight, and weight is 3, 3, 4, and parent is 1. And from 1 we can move to 2 also, and 2 is also not visited yet. So we will insert 2 also in this priority queue. And from 1 we can move to 2 with weight 1. So we will insert 1, 2, and parent is 1. From 1 we can move to 3 also. So we will insert 3 also in this priority queue, and the weight will be 5, this 5, 3, and parent will be 1. Now from this priority queue, we will take out the another element with minimum weight, that is now this 1, 2, 1. So we will take out this 1, 2, 1. So first we will insert this edge in our MST list. So 1, 2, and we will add this weight to our total sum, that is 1. So 0 plus 2 plus 1, and we will mark this second node as visited. So we will mark it as visited. Now we will look at the neighbors of 2. So from 2 we can move to 3 as well as to 1. But as 1 is already visited, so we will ignore 1. So we will insert 3 in this priority queue, and the weight will be 1, this 1. So we will insert 1, 3, and parent will be 2. There is no another neighbor of 2. So now we will take out another element from this priority queue. At this time, we will get this element 1, 3, 2. So first we will insert this edge to our MST list. So 2 comma 3, and we will add this weight to our total sum. So that is 1 plus 1, and we will mark the third node as visited. Now we will look at the neighbors of 3. So from 3 we can move to 4 and 2 and 1. 1 and 2 are already visited, so we will ignore 1 and 2. So we will insert 4 in this priority queue, and from 3 we can move to 4 with weight 4. So we will insert 4, and node will be 4 and parent will be 3. Now we will take out another element from this priority queue with minimum weight, that is this element at this time 240. So first we will insert this edge in our MST list, so 0 comma 4, and we will add this weight to our total sum, so plus 2, and we will mark fourth node as visited. Now we will look at the neighbors of 4 which are not visited yet. So from 4 we can move to 0, 1, and 3. But 0, 1, and 3 are already visited. So we will ignore all these nodes, and we will not insert any node in this priority queue now. Now we will remove all the elements from this priority queue one by one. But we will not do anything with these elements because all the nodes are already visited. So in this way, we will get a total sum minimum spanning tree weights, that is 2 plus 1 3 plus 1 4 plus 2 6, and this is the edge list. And if we create a minimum spanning tree with these edges, then it will look like this. We will have an edge from 0 to 1, and weight will be 2, from 1 to 2, and weight will be 1, and from 2 to 3, and weight will be again 1, and 0 to 4, and weight will be 2. And if we add all these weights, then we will get 6 as the total sum. So in this way, we can get a minimum spanning tree with the help of Prim's algorithm. Now let's implement the code. So here we have given the graph in the form of adjacency list and number of vertices as V and number of edges as E. And here we need to return the sum of weights of edges of minimum spanning tree. So here first we will take a priority queue. So let's have a priority queue. As here we just need to return the sum of weights of the edges of MSC. So we will store only node with its weight from its parent in this priority queue. For that we will take a class named as pair. So let's have a class as pair. In this we will take node and its weight from its parent. Now let's have a constructor and we will initialize our node and weight like this. And now let's define the type of this priority queue as pair. So now we will take a boolean visited array. So let's have array and the size of this array will be equal to the number of vertices. Now let's add a first pair in this queue. As I already explained, we can start from any vertex. So here we will start from the 0th vertex and its weight will be 0. And here we will take one variable, let's say total sum, that we will return in last, and initially it will be 0. Now we will iterate over this queue until queue be empty. So let's have a while loop over this queue. Now from this queue we will remove all the elements one by one based on the minimum weight. So here we need to add one comparator on this priority queue. So let's have a comparator over this priority queue and that will be like this. So it will give us the edges with minimum weight first. So now we will remove all the elements from this priority queue one by one. So let's have the pairs. Let's say current pair and queue.read. Now this current pair contains the node. So let's have a current node and current pair dot node and its weight from its parent. So let's have a weight from pair variable and current pair dot weight. Now first we will check if this node is already visited or not. So if node is already visited, then we will not do anything and we will return back. So we will do continue. If node is not visited, then first we will mark it as visited. So let's mark it as visited. And then we will look for the neighbors of this current node. So let's have a for loop to get the neighbors of this current node. And this neighbor contains two values. One is the neighbor. So let's have a neighbor, current neighbor. That will be neighbor dot get 0 and its weight from its parent. So neighbor weight from parent. Neighbor dot get 1. Now we will add this neighbor in the priority queue with its weight from its parent. And we need to update our total sum. So let's update our total sum also here. Total sum will be equal to total sum plus weight from parent. And in last, we will return our total sum. So that's it. So now let's try to compile this. So this is fine. So now let's try to submit this. So this is also fine. Now let's have a look at the space and time complexity. So here we can see that we are using a priority queue and this boolean visited array. So we can say that the space complexity will be E plus V. But as E can be a large number as compared to vertices, so we can say that the space complexity will be big of E overall. And the time complexity of Prim's algorithm is E log E. So that's it. Thanks.